Então, meu nome é Diego Chrysosthemos, and today we will talk about this article, quantum coherence versus interferometric visibility in a biased Mach-Zehnder interferometer. This is written by me, my co-worker Marcos Bassos, and my advisor Jonas Mazier. First, I will talk about the double-slit experiment. You have an electron gun and a wall with two slits, 1 and 2, and a backstop, and a movable detector. So you can change the position along the backstop and proceed the measure about the electron in reach the backstop. So we can perform two simple experiments here. First, we consider one closed, one slit closed, for example, the second one. Turn on the electron gun and change the positions of the detector at the same amount of time. And you can plot the graph P1. So you have this pattern, and you can procedure the same experiment, but closing the first one now. And now you have the P2 graph here. This graph A, B, gives us the notions of the pattern, behavior. Particle behavior and nature. Now, the more interesting is when you open the two slits and procedure the same detection, and now you have the graph C here. So now you have the interference pattern. This gives us the notions of wave behavior of nature. The first one, you know the slit that the electrons goes through. In the P1, you know is the slit 1, and the P2, you know the electrons goes to the 2 slit. But in the graph C, you don't know about the path of the electron. These notions give us the Born to state his complementarity principle. So you have two behaviors of nature that are complementarity, like position and momentum, time and energy, and as we show for you, is particle and wave. So if you know about the one aspect of nature, for example, position, you have the more uncertainty about the other, momentum. Now I will talk more specifically about the particle and wave. So the researchers find these relations that you can quantifying these two aspects. For example, P is predictability, stands for the quantifying the particle behavior, and V stands for the visibility. You can quantify the wave behavior of nature. So it's in equations, you have the maximum value for 1. When the system is pure, you have the equality. You can make the same idea with this other relation where P stands again for predictability, gives us the behavior of particle, and C stands for the coherence. You have a relations for different functions of coherence, for example. So these relations, it's about it's calculated by the state of your quantum system. And the maximum value, it's a constant functions that depends only the dimension of the system. The setup that we use it here is Mach-Zehnder interferometer. So you have an incident beam here, a quantum system, photons, for example, and you have a beam splitter, and divide your beam in two ways, upper way in a way down. So the beam here goes to the mirror, here too, and are reflected. In this path, you have a phase shifter that gives the notions equally that the double-slit experiment. You change this phase, you can have the interference pattern between these two paths. So the beams are recombined and pass through another beam splitter and divided again and goes through different detectors, D0 and D1. So what we make here is choose a bias beam splitter that you can change the amount of quantum transmitted and reflected. And we have the bias beam splitter here and here too, so you can change these quantities. Here's the wave functions of each step. So we use these notations. If you have a horizontal move in this Mach-Zehnder interferometer, you have the cat 0, and if you have a vertical move, you have a cat 1. So the initial state here is C0 is equal cat 0. After the beam splitter, you have this state. After the mirrors and phase shifter, you have this state. And after the second beam splitter, you have the state given by this for expression. So by Born's rules, you can obtain the probabilities of these two wave functions. So you have a probability of the quantum reach the detector D0 and reach the detector D1. So these two expressions, of course, depends on the transmissions and reflections coefficients of the two beam splitters. So in the literature, you can find that visibility can be found using the maximum probabilities and minimum probabilities in this form with these expressions above. So these two expressions for V0 stands for detector D0 and V1 for detector D1. So these two expressions depends of the two coefficients of transmissions, the bias beam splitter 1 and 2. The respectively expression for predictability is given by 9, and you can perform complementarity relations. V0 square plus V0 square, you have equals 1 because we are considered here a pure state. Now let's choose some cases of study here. So first, I choose just one case here, but you can find another case in the article. And if you choose the two beam splitters equally, you have a generic T and generic R. You can find that visibility is equal 1 and predictability is equal 0. When I talk about the predictability and visibility in this setup, if you know the path inside of the interferometer, you know the which way, they say about this two, which way. And if you have the more uncertainty about the path, you have the visibility, so you don't know where the photon is going through. So in these expressions here, you have a predictability of 0, you have a visibility 1. Okay. But now let's look for this case. If you have the transmission much greater than R, you have almost all the quantums going through the way up, or if you have a reflection much greater than transmissions, you have the way down. But if you look, you expect that predictability is almost 1, right? You have almost the quantums going through the one way. So these expressions give us a wrong idea about the complementarity relations. So now we use these relations about the coherence and predictability for using the state of the system, right? So the result gives us we obtain for the C2. So we have these conditions. Now, if we look for the transmissions almost 1, close to 1, as we said before, we're gonna find that the coherence is almost 0, as we expected, because coherence quantifying the visibility too, and predictability almost close to 1. Complementarity relations, of course, is 1 because we have a pure state again. We plot the results in a graph. So the orange line, we have the predictability, and the blue line we have the coherence. So when the theta is almost 0, we have the transmission close to 1, so we have the predictability close to 1, as we expected, right? So the coherence is 0, and if you change the angle, you have the what is expected for the idea of the experiment. And for the black dots, we have the visibility. So that gives us a wrong idea, because in this case, the visibility depends of the transmissions and reflections of the states for the visibility. That's it. Thanks.